All right, so flowing, actually, this is kind of a nice picture of what's happening here, right? So into each of these control volumes and out of each of these control volumes flows the moles of helium. So that's what we have in and out. I'll just write A for the helium instead of HE, it's just a little easier. Excuse me. So we'll figure that out, but for both of these, that's what's coming in is the flux times the area. And in fact, for both of these, what's going out is the flux times an area. And because we've made this thin in the direction of transport, both of these are going to be evaluated at some, let's see, coming out is y plus delta y. Coming in is evaluated at y. So this is true for both of our systems. We're at different spatial locations, obviously, for the silicon dioxide and the Pyrex, but we have the terms that we need to fill into our conservation law. So our conservation law says in minus out plus anything that's generated equals an accumulation. We have this thing operating at steady state. We don't have any changes with time, and that's nice because then we also, in the lack of generation, we don't have any generation of helium inside of this glass. So without an accumulation and without a generation, that means our total concentration is constant, which is nice. And it means we just have to balance what flows into these control volumes with what flows out of these control volumes. So we need to balance the flux coming in and the flux going out. So for the Pyrex, because that's the first thing we encounter here, we're going to have the flux of A evaluated at y minus, right, the out term is y plus delta y, times AS. That's all right, because we know that surface area actually doesn't change. We picked, again, that rectangular prism, so as we move up and down in y, we don't expect any change in the surface area. We don't need to evaluate the surface area at y plus delta y or y. In fact, what we can do is surface area and that equals to 0. And so at this point, we could just cancel out our surface area, but let's just replace this with our delta x, delta z. And then divide by the control volume. So we define this control volume of the Pyrex as delta x, delta y, delta z. So we're looking at this per volume, and we can cancel our like terms, delta x and z, and we see we can take the limit of this function to find, now we have state 1 minus state 2, so this will be negative d and a. The delta y is we take the limit and deltas go to 0. So we just landed on essentially the same thing that we were looking at as far as the momentum flux. And let's take a break now and turn to the silicon dioxide and look at how this derivation will be similar. So we have in minus out equals 0. Into this is, again, Na AS evaluated at y minus the flux of A times the surface area evaluated at y plus delta y. All right, so the surface area does not change, and in fact, in this case, we let the surface area be large, so we're not going to replace that with anything. We're just going to write this as the surface area times the change in the flux over that delta y. And now we divide by the volume that we defined. We defined this volume as AS delta y. How convenient, because now we can let the common terms cancel again, and we've landed on the same result. So that's what I mean when I say you just need to make this thin in the direction of transport. Everything else will work itself out. Terms will cancel if you've done it right.